Welcome back, everyone, to the Algebraic Graph Theory seminar. This week we have Chris Godsil talking about the rooted product.
Okay. We had late cancellation, so I'm the substitute teacher. Before this seminar went online, usually it was chaired by one of the grad students, and there was a rule that if they really couldn't find someone else to give a talk, then they would call on me, which gave them an incentive. And apparently that dispensation is still in effect, so here we are. So I want to talk about stuff. In some sense, this is related to David Goss's talk in the workshop a couple of weeks ago. So physicists are interested in the situation, continuous quantum walks on a graph. We have a sort of base graph X, and you attach some infinite paths to some of the vertices. I'll draw some pictures in a moment, and you'll see what's going on. So and that's what I want to talk about. Okay. But I'm going to go back in time. So when Brendan, McKay, and I were graduate students, Brendan started computing character polynomials of trees. So we generate a lot of data. We look into data, and we noticed that for some trees, the character polynomial was symmetric. So the coefficients are symmetric about the middle. So in particular, for example, that meant that since the first coefficient is 1, the last coefficient is plus or minus 1, so the tree has a perfect matching. And so, as you can see there, there's some examples. First few examples: the path on 2 vertices, path on 4 vertices, path on 6 vertices, and you can see the character polynomials there. And as I said, they're symmetric. And so, what we noticed was that all the trees that had symmetric character polynomial had the structure. You started with a base tree, and then you added a new vertex of valency 1 to each of the vertices already there. And so you've got a tree on 2 end vertices. And that new tree obviously has a perfect matching, so its character polynomial is determined as plus or minus 1. So to deal with this, we introduced what we called the rooted product. So for rooted product, we start with a base graph X on n vertices and a sequence of graphs y1 up to yn. We can think of as rooted graphs, and then we merge the root at each of the graphs yi with the corresponding vertex of X. Okay, and that's what I said there. And we proved that if the graph is a tree and the character polynomial is symmetric, then the tree is a rooted product with a sequence of K2s. Okay, and so the examples up there, these examples are showing you exactly what happened. Yeah. So that's nice. In fact, it's a little stronger. We proved that if the number of you don't need the polynomial to be symmetric, you just need the second and second last terms to be equal, or first and last terms to be equal, so both matching, and the second and second last terms to be equal, but that's not important now. So the question is, well, to prove this result, we need information about the character polynomial of the rooted product. I have to throw in a snarky remark here. The definition of rooted product on the Wikipedia page was wrong because it insists that the yi's are all equal. We don't require that. So I want to get the character polynomial of this rooted product. And so to do that, I'm going to define 2 diagonal matrices. The first matrix has the character polynomials of the yi's as character polynomials of the y sub i's as the diagonal entries, 0 or square. And D1 has the character polynomials of yi's with the root deleted. Now, if y is a graph with 1 vertex, its character polynomial is t, and the graph with the root deleted will have character polynomial 1, just in case you start to worry. So the theorem that we proved is the character polynomial of the rooted product has got this form. So there's some products of the character polynomials of the graphs y with the roots deleted, and then there's this thing here. And so normally the character polynomial, you're thinking ti minus a, and so ti is being replaced by this bit. So this is a diagonal matrix, and the ith diagonal entry is the character polynomial of y sub I divided by the character polynomial of y sub I with the root deleted. For if you take yi to be k2, then the formula of the Coase polynomial is what we see here. And so from this, you can show quite quickly that the Coase polynomial of the rooted product of a tree with k2 is symmetric. Now, it's not true in general for an arbitrary graph that the Coase polynomial is symmetric. It's a rooted product, but that's the counter example that would be this graph has symmetric Coase polynomial is not a rooted product. Okay, so as I said, Brendan and I proved this result. Now, I'm not going to prove it today. I'll give you a start though. So I want to focus on a special case because there's something that I'll be using quite a bit. So if I just take a graph X and a graph Y and merge a vertex, say the root of Y with the vertex in X, okay, that's a rooted product. I've got a sequence Y. The first thing is a graph Y. The second thing is the remaining graphs are all K1. So the theorem tells us that when you decode it, you have to push through a little bit. You get the following expression for the Coase polynomial. You get the Coase polynomial Y drop 1 times the Coase polynomial of X. The Coase polynomial of Y times the Coase polynomial of X drop 1, and then T times the product of those two Coase polynomials. So this graph here is a one sum of Y and X, and this formula of the Coase polynomial goes. Well, I got it from Schwenk. It's probably due to him. I'm fairly sure it's due to him. I just haven't checked. Now, so my point is that this formula for the one sum, which we're going to use, which has a number of proofs, is a special case of the formula for the rooted product. And as far as proving that the rooted product formula is correct, basically you just use the result for the one sum and induction on the number of vertices. So it's reasonably straightforward, and you can always look it up if you really care. And since I like examples, I did another example with a rooted product. This time I'm taking the path on 3 vertices, and I'm taking Y to be path on 2 vertices, 1 vertex, 2 vertex. And so there's script D1 in inverse D as shown there. The graph we're getting is going to be the path on 5 vertices. I picked this example so I would know if I got my calculations correct or not. So this is the formula given by the formula I gave you for the Coase polynomial of the one sum, of the rooted product. And when you unpack it, you get t to the 5th minus 4t cubed plus 3t, which is indeed the Coase polynomial of the path on 5 vertices. So not lost yet. So that's the rooted product. Okay. One point about this, I guess I'm making implicitly, is a lot of this stuff was done well before anybody was thinking about quantum computing. That's certainly part of it. So now we get to the situation that the physicists were interested in. So this starts with work by Andrew Childs and by Dave Godsil. So they're considering a situation as follows, so what we're calling graphs with tails. So we have a graph X, we have a subset C of the vertices with the size little c, and we're going to have a sequence of paths. Y is going to be actually, I've got this is slightly wrong. Let's fix it. It should be the idea is that Y consists of C copies of the path of n vertices and a bunch of K1s. And so for the example I've drawn here, we're going to have 3 copies of the path on n vertices and the rest is K1s. So this here is the graph. This is a graph with tails. Now the physicist's idea, and I'm not going to be doing any real physics or even any quantum walks much today, but I'm focusing on the spectrum of this graph. But the idea, physicists tend to think of it, you have some signal coming in along this tail, and there's some stuff scatters back from along the input and goes out along these two. So you view this as an input channel and this is 2 output channels. Now there's devil's hiding in the details as usual, but that's the setup. So this is the graph they're dealing with. And the claim is that they can use continuous quantum walks on graphs like this to construct unitary gates, which will be a basic tool for quantum computation. Now, all I'm concerned with today is information about the spectrum of graphs like this. So that's a graph with tails. And the point is, it's a rooted product. And so I need one piece of a couple pieces of information. The first thing is the character polynomial of the path length vertices satisfies a 3-term recurrence. You can view this as a special case of the one sum, where you take a path on n-1 vertices and you sum it with the path on 2 vertices. And if you do that, you'll get this formula. And we get a ratio which looks like this. Now, I mentioned this because it's going to turn up in a moment. So the claim is if we use the formula for the rooted product, then the character polynomial rooted product is going to be copies of the character polynomial of the path on n-1 vertices, okay, times, and the matrix is just Ti minus the adjacency matrix minus this ratio, psi n, minus ratio, times a diagonal matrix with ones on the entries in C and zeros elsewhere. Okay, so that's the formula we get from the rooted product formula. So we can write down the character polynomial. Now, it's fairly clear to get information out of this, it's going to take some effort, but the point is we do have an explicit matrix. We can simplify a little bit because what we're doing is we're taking Ti minus A, let's do this in blue just for fun. And then we're subtracting a diagonal matrix. The point is if I divide through, well, what I claim is if I divide through by the determinant of Ti minus A, which is the character polynomial of X, then what stays inside the determinant is this. And the point about this is that this matrix here, it's got the columns corresponding to the entries of C are non-zero, but the other columns are 0. So this matrix here is block diagonal, block triangular, and so it's so we can actually looking at the determinant of a C by C matrix now, rather than an N by N matrix. So we do have some progress, and for what the physicists are doing, you're not adding a huge number of tails, 2 or 3 or 4. So this is just a 4 by 4 matrix at worst, and so its entries are going to be messy, but they're under control. So what I'm trying to point out here is you do have some hope, and for computational purposes, this is just fine. Okay, now the scattering connection, I'll explain how it arises. I'm not going to spend any time on significance. The tool we need is the Schur complement. Now, I didn't always get confused about the Schur complement because I'm never sure what's the complement, what's the rest of it. And so I usually work things out as I need them, but I actually try to get it right first. So the assumption is we've got a matrix in block form. The matrix is invertible, and what I'm going to do, I'm going to assume that the 2-2 block is invertible. And the Schur complement, well, the formula tells you that the 1-1 block of A inverse is given by this. Okay, and so this enables you to, in some sense, well, compute the inverse of A. If you're given the inverse of A2, you can compute the inverse of A1 with less effort than might be required otherwise. Of course, by one of the rules of numerical analysis, you shouldn't be computing the inverse of A anyway, but that's another story. And so in this particular case, we're not really inverting A, we're inverting this mess, Ti minus A minus our diagonal matrix. And the Schur complement in this case is given by this. Now, this is a little c by little c matrix. And all I'm claiming is that's the Schur complement, okay? And it's going to come back to haunt you later on. This will give rise to what physicists call the scattering matrix. Now, if I'm going to do anything with that, I certainly need more information about psi n. Also, the physicists are concerned about the case when the tails are long. So you want to be thinking about the case where the limit of psi n then goes to infinity. And we'll come back to that. Now, we can say something useful about the eigenvalues of our rooted product. Now, here I've just started with the baby case. You can call this a tadpole. So just adding one tail, but what I'm going to say will apply to the general case because it's going to talk about how the spectrum of X changes when you add a tail, and there's nothing that's saying that X doesn't already have tails. So what I'm describing is how the spectrum changes when you increase the number of tails, if you like. Now, using the one-sum formula, the character polynomial of this graph is given it's 5x times 5 correspondent of x times correspondent of Pn minus correspondent of x drop A times the correspondent of the path n minus 1 vertices. And so if t is a 0 of this, then we're going to have these two ratios being equal. So for any eigenvalue, so I probably should call that theta. Let's not, that's fast. That's one color. Let's call that a theta. So, and I say my host effort there. So I'm going to have the ratio 5x drop A of 5x at the eigenvalue. It should be equal to of 5Pn over 5Pn minus 1 at the eigenvalue. So that's the condition we need to, that identifies where the eigenvalues occur. Now, my claim is the number of eigenvalues z greater than 2 is independent of the size of the path. Okay, so as you increase the length of the path, the number of eigenvalues greater than 2 doesn't change. Okay, now just by, I think everybody here knows, but the eigenvalues of a path all lie in interval -2 to 2. Okay, so most of the eigenvalues of this graph can end up being an interval -2 to 2, but there may be some number outside. Well, in fact, if you start with n equals 0, you look at the eigenvalues of x that are outside the range -2 to 2, and in a sense, those eigenvalues stay, although they spread out. Now, how do I prove this? Well, I prove it by a picture. That's fun. The first thing I want to look at the graph of 5x drop A over 5x. Now, this is a rational function, so you can go back to your calculus and expand it by partial fractions. When you do so, you discover, using spectral decomposition, that the numerators in your partial fractions are all positive. So the partial fractions equal sum of something positive over t minus some eigenvalue. And so that tells you that the derivative of this ratio is negative everywhere it's defined. And so then you draw the picture, you know that there are so the asymptotes, the vertical asymptotes are at the zeros of phi x, they're the poles, and the crossings of the x-axis give you the zeros of 5x drop A. And so you imagine there's the graph of 5x drop A and 5x. Now, on the other side, we had phi of Pn plus 1 over 5Pn, or phi of En over 5Pn minus 1. That's not of this form, it's upside down. But the point is, again, by elementary calculus, if the derivative of f is negative, then the derivative of 1 on f is positive. And so that tells me that the graph for pi n and 5pi n or 5pi n minus 1 looks like this. So it's asymptotic to the curve y equals x, because if this is t to the n over t to the n minus 1 for large n. So it's going to be asymptotic to t for large values of t. And the other eigenvalues, well, and the graph's positive with asymptotes at the zeros of pi of n minus 1, so you get a graph like this. Now, the zeros of our x with our tail attached, we get by putting this picture here on top of this picture. And given I drew this by hand, I'm not about to try it, but if I put this picture on top of this picture, the points where the green lines intersect the black lines give me the zeros of z. Okay, and so if you stare at that long enough, you then see that my claim follows. The number of eigenvalues outside interval -2 to 2 doesn't change. Okay, so we will have some eigenvalues out there. Most of them, as I said, are in the interval -2 to 2. Okay, so we've seen, so the point now is that the spectrum of a graph of tails is given by a rooted product formula, okay, which is a little bit of a mess and involves these ratios, 5Pn minus 1 over 5Pn and things like this. And so I want to come back and think about these things for a while. So well, we're thinking about generating functions, I'll explain it first, and then Bessel functions, which you may not expect to see. So there's a background thought here is that the physicists will say that when they're working with their graphs with tails, that they're really thinking of those paths, those tails as being infinite. Okay, and so then you say, well, how are you going to implement that? And I say, we'll just say, they agree and say, we'll use a large finite path. Okay, now I'm going to first explain, in a sense, why that is correct and why that is a good idea, and then I'll explain why it's a bad idea, and you can make up your own mind at that point. So I'm concerned with this ratio phi of Pn minus 1 over phi Pnt. Now, the tool I need here is that the 1,1 entry of Ti minus A inverse is actually just phi of x drop 1 over phi of x. Okay, because when you delete the Carrick's polynomial T minus A is Carrick's polynomial of x, and if you delete the first row and column, you're looking at Carrick's polynomial of x drop 1. Okay, so we have this. Okay, so Ti minus A. Now, I can rewrite Ti minus A as T inverse times I minus T inverse A inverse. And the thing here is that the 1,1 entry of I minus T A inverse, which is given by this mess here, this is a generating function. It's a generating function for the walks in the graph, which start at 1 and finish at 1, and you by length. So it's the closed walk generating function. So I'm basically going to take the view that this is a generating function. Technically, I should be expanding a 1 on T, but it's not worth the fuss. So I'm just going to view this as a generating function. And if I was pressed, I'd need to go back through this argument to make things clear. But we can still, for summary, is we can view this as a generating function for closed walks. In particular, it's completely determined by the knowledge of the number of closed walks of length n for each n. That is true, and that's what we need. So we know that's a walk generating function. The other thing you see is if I let n increase, well, it's still a walk generating function. And what we're doing is counting the generating function for the walks in the path, which start and finish at the left-hand end vertex. Now, if I look for the closed walks of length 100, a path of length 1,000 or a path of length 2,000, I'll get the same answer. So the initial terms of these polynomials agree, and I did it explicitly here. If you look at the difference, well, you just do a straightforward calculation and you get this. And so the interesting thing is the numerator here, 5Pn squared minus this, is actually equal to 1. And it's a fun exercise, so I'm not going to go into it. So this is telling me that these two things agree up to terms of order something like 2n or 2n plus 1. Okay, and so that's enough to verify that limit exists as a generating function. Or you could if you like, where you could view ourselves as working over the ring of Laurent functions. And we will be working over things a little bit more complicated than reals and complexes eventually. So, but in any case, so the point is the limit exists. Okay, in the sense that as a series of generating functions. Now, you can also show the limit exists if you view these things as functions of t, provided t is greater than equal to 2, or absolute value of t is greater than equal to 2. That won't play much of a role, but the limits exist as generating functions or as formal Laurent series. They also exist as functions for suitable values when t is large enough. Okay, so let's put this to work. The physicists say they want to think about the infinite path, so let's do that. So we have I'm going to write the infinite path. And now at this point, they're concerned with continuous quantum walks, which are given by a matrix U of t, which is x of ita. And the thing you care about is the 0R entry of this. So I've written that out as painless. And now I'm making a definition here. This is something that's proved in my book on algebraic combinatorics. We can write the 0R entry of x of TA as this. So r plus 1 t to the r times a series t to the 2m over m factorial m plus r plus 1 factorial. Okay, now this is straightforward counting. Basically, all you need to count the walks. You have an infinite path. You want the walks of length n that start at 0 and stop at a vertex r. That's very in steps. Okay, and so you want to write down a generating function. So it's an exercise in the reflection principle. And so you deduce this. And so I've done something. And well, I'm concerned about the transition matrix for the quantum walk. So I want FR of IT. And so I've written that out here. And we never needed that. So why does this matter? The point is that FR is essentially is a Bessel function. Now, Bessel functions, there are Bessel functions of the first kind and there's Bessel functions of the second kind, and there are two of each, so there's lots of choices. But I'm going to say these are basically just the standard Bessel functions. Now, the Bessel functions I denote as usual by G sub R of t. You can come at them in two ways. One is there a solution to a differential equation, and there's the equation written out for you. Okay, it's just a second order differential equation, but with polynomial coefficients. And R here, or for us, R is going to be an integer. If you're an analyst, you can allow a bigger range of values, but we're not going to go there. Now, it's also the Bessel functions are given by a series, and here's the series. Okay, so in principle, you could work out the series from the differential equation. Okay, which is probably the way it was first defined anyway. So, so we have this sum. So, the point is, this is just a tidied up version of what I was calling S sub R. And so the theorem we get in consequence is that UT, which is for the infinite path, the 0R entry is given by a fudge factor times the Bessel function. So this means that we can compute the probability if you imagine a continuous quantum walk on the infinite path starting at 0. And then we can compute the probability that at time R, that when you measure at time t, the on vertex R is given by this. Okay, so this is the Bessel function. Now, that's well and good. You might say all I'm doing is giving U of t another name. There are some information, or is some information we can extract from this. First thing, it's known that the zeros of the Bessel function. Well, there's a 0 at 0. In fact, if you think of the graph of the Bessel function in general, it looks like a graph of the sine function, but dying off. It goes to 0 like 1 over 1 on root t. But that looks a lot like a graph of a sine function. But so there's a theorem that says the zeros are positive, real, and countable. So it is 0 often. Okay, and there's even information about the size of the gaps between consecutive zeros. Another result, which proved by Siegel, is that the different Bessel functions don't have any common and positive zeros. So one consequence of this is you can't get PST on the infinite path, which is not a surprise, but it's and it's much easier. Well, actually, it's not quite clear how you would prove it, since the standard approach we use wouldn't work. So, the information about Bessel functions can tell us something about the continuous quantum walk. Okay, so we've seen if my ratio is 5pn minus 1 over 5pn. Okay, in the end are connected to Bessel functions. Okay, and so I have a name for and so there could be some information. I want to get more information about this limit 5n minus 1 over 5n. And so for this, I'm going to consider what they call chains. And I can draw a little picture just to make it clear. So the picture, and there'll be another same picture appearing slightly better drawn later. So I'm thinking of a situation where I have some graph X with a pair of vertices A and B. And I just join I just identify the B vertex. Well, I build these things up by taking a new copy of X and identifying the, I got that, oh, God, mad. So I just identifying the A vertex of X with what the B vertex of what's left over. So I get what I'm calling a chain. Now, the best example of a chain is take X equals K2 and you get the path length vertices. Okay. And so that's what I'm calling a chain. That's what I'm working with. And so I want information, in the end, I want information related to the correct polynomials of these graphs. And the interesting thing is you can have some fun with it. So I want to find an explicit expression for this limit 5pn minus 1 over 5pn. Okay, and so here's my drawing of the chain again. So as a question, so the only tool here, definition here is I'm building up my chain from copies of a block. So I think this is a connected graph with rooted at two vertices A and B. Okay, so it's a triple x comma AB if I need to be precise. And the question I'm asking first is, what is the Carrick's polynomial of this graph? Or can I say, give you something concrete information or formulas for the Carrick's polynomial of these graphs? And this is what we're about to do. Well, for case m equals 2, we're just looking at a one sum. Now, I could have started with 2 copies of x, but I started with the graph y. So you can think of y as being x for now, or it might be a chain of m minus 1 copies of x. Just there's a graph y and a graph x. Okay, so this is our generic procedure. We're taking some graph y, and we're taking one sum with x. Now, if we do that, then we get 2 formulas. So this is now, this is my private working notation. So every uppercase variable here should have a phi comma t wrapped around it. So I'm using z for the Carrick's polynomial of phi of z comma t, and x, the Carrick's polynomial of phi of x comma t. So I'm using the name of the graph for the Carrick's polynomial. And so this is the one sum formula. Okay, this is just our one sum formula. We're joining x with Carrick's polynomial of x times, Carrick's polynomial of x times Carrick's polynomial of y with b deleted, Carrick's polynomial of x with a deleted times Carrick's polynomial of y times t times both. And so we have that. Now, for my amusement, I've also written down the formula for z sub b. In a sense, what I'm trying to do is work out will be the generating function for closed walks in z that start at b. So I would need these 2 things. And so I have those 2 equations, and I'm going to do what I view as the obvious thing is to write these in matrix form. So I've done that. And then I observed that the matrix can be factored, which is sometimes useful. So I have that. At least this is, I can never remember this, but I can remember this. So I have x drop a, x drop b, x drop ab, there it is. And then this little fudge factor there. So what this tells me is how this term changes when I add an extra copy of x to my chain. Okay, so if I have the generating, in other words, if I have the generating function for closed walks at b in y, I can get the generating function for closed walks in z at b. Okay, so that's okay. So we have that. So it'd be convenient to give this guy a name. So I'm calling it psi, and I'm giving the identifying 2 vertices. And so the conclusion is that the ratio that z comma a is equal to phi to the m times t comma 1. So I have, and so I can, in a certain sense, I've reduced my problem of computing the walk generating function for z at the vertex a to the problem just of determining this. And that, yeah, we'll come back to that a little bit. I can also write this in a slightly expanded form. I've written out that. It's not entirely clear why. So let's look at an example. If we look at K2, which is the obvious one, then you calculate without too much trouble, but psi 1, 2 is just this matrix here, T minus 1, 1, 0. And so the conclusion we get is that phi of PM, the Carrick's polynomial of PM plus 1, Carrick's polynomial of PM is equal to this matrix to the M times T1. Now, this is probably a threat more than a help, but if I want to compute the mth power of a matrix, then what we do is we use, we know the answer. Well, in this case, this matrix is not symmetric, but it is diagonalizable. Its eigenvalues are distinct. So I know that when I unpack this, I'm going to get my formulas for PM plus 1 and PM as linear combinations of powers of the roots of this guy. Okay, and since I only care about the limit, I can often fudge my way around the constants. But so the point is, I know that the answer. So I know that my ratio phi of PM minus 1 over phi of PM is going to be a linear combination of power of the nth powers of the roots of this, and I'll be able to use that to compute the limit as m goes to infinity. Before doing that, I'll just do one more example, which is actually this graph used to be called Harari's random graph, but because when you draw a random graph on the board, this is what he drew. So I'm just taking well, K4 with an edge deleted or a cycle C4 with an edge added. So there's my graph, and I'm using 0 and 1 as the vertices of attachment. And then you can calculate that psi is given by this mess here. Okay, so this is the Carrick's polynomial of the P3, this is the Carrick's polynomial of K3, this is the Carrick's polynomial of P2, and this is the Carrick's polynomial of the whole mess. Okay, and so this here is psi. Okay, so we have psi. Now you compute the trace, and I got that right. The determinant of psi is given by this, which if you look at it as t squared times t plus 1 squared, and I can't resist remarking that in fact the determinant of psi is always a perfect square, and so that doesn't play too big a role. But the point is that I have all this information, so I can get a formula for the eigenvalues. It's going to be a solution of a quadratic with polynomial coefficients. And so it's going to be polynomial plus a square root of another polynomial. Now that's not nice, but it could be a lot worse. So we'll actually have an explicit formula for the eigenvalues of this graph. Okay, provided we can deal with the eigenvalues of x itself. Okay, so the point I want to make though is that our operation that we're using, multiplying things by two matrices, occurs under another name. The terminology is linear fractional maps. Now, the way this arises is in projective geometry. The question is, you know that the collineations of projective space are basically given by linear maps and field automorphisms, but it's basically linear maps modulo the scalars. Okay. Now, the question you ask is, suppose I have a line in projective space and I'm looking for the collineations of the space which fix the line. What happens to the points on that line? Now, often in projective geometry, your field is finite, so your line's finite. And so the mapping on that line is a permutation group. Now, how big is that permutation group? Is it the symmetric group? Okay, so this is the question we're addressing. Now, it turns out that you can represent the maps on the line as so-called linear fractional maps. So you start with a matrix with non-zero determinant, and then we define the linear fractional map tau sub A to be the map which sends x to ax plus b over cx plus d. Now, the geometric intuition is the points on the line correspond to ratios x over y. And so you only take y equals 1, but it's useful to take y equals 0. So I want to work the line is indexed by the points in the field together with infinity. Okay, so geometrically, the points on the line correspond, think of them as x over y's. In terms of the algebra, they're given by vectors x over y. And so the matrix acts on the vectors and the linear fractional map acts here. Now, the point is that if I replace A by, say, 2A, tau A doesn't change. So technically, tau A is not a matrix. This is not a matrix representation of a group. This is a permutation representation at best. And the point then we see is that phi sub AB of x is giving us a linear fractional map on rational functions in T. So now the relevant question turns out to be, what are the fixed points? Because the limits I'm dealing with, phi of n minus 1 over phi of n, turn out to be fixed points for the linear fractional map. Now, tau sub A fixed as x is just this equation. Ax equals a times vector equals lambda times vector. And for my amusement, I've written this out a little bit. I don't know where that 0, 1 came from. That should be, that's the problem. Right. That's 0. So the eigenvector equation just says I want a minus lambda b c d minus lambda applied to x1 to be 0. Now, this is not something we tell our undergraduates, but that means that the vector a minus lambda b is orthogonal to the vector x1. Now, the vectors orthogonal to the vector uv in R2 are the vectors scalar upwards of v minus u. Okay. And so that tells me that x1 must be a orthogonal, well, in this case, orthogonal A minus lambda B. So that means x1 must be a scalar multiple of B over lambda minus A. Okay, so we get the entry of x. So I've determined the eigenvector. Now the point here, the real point here simply is that the eigenvector is determined by the eigenvalue. Okay, and there's a very simple formula. Okay, so we have that. So, so in other words, if I'm trying to determine the limits of my fixed point linear fractional map, well, what this is telling us, the fixed points correspond to the eigenvalues of the matrix A. Now it's a 2 by 2 matrix, so this tells you that the linear fractional map, the fixed has either 0, 1, or 2 fixed points. So in particular, any linear fractional map which fixes 3 points must be the identity. And in fact, you can show that a linear fraction, given 2 triples, there's a linear fractional map which takes 1 to the other. So this gives you a proof that the linear fractional group is sharply 3 transitive. That's the group theory, which we're not doing. Okay, so the idea, so the point now is that I can get my fixed points from the eigenvalues of my linear fractional map, or my eigenvalues, my 2 by 2 matrix. And so if we do this for K2, the eigenvalues correspond as x squared minus tx plus 1, and the eigenvalues are given by this. And so that tells me the limit, when you work it out, of this ratio is given by this function. Now, it's an algebraic function. It could be a lot worse. I mean, you can actually work out coefficients and things from this, of course, and basically involving Catalan numbers. But so we have that limit explicitly. And for your amusement, I also did the same thing for K4 minus an edge. We get that the, so there's psi, and the eigenvalues are t cubed minus 4t minus 2, plus or minus the square root delta, where delta is given by this mess. Okay, so this factor, I just realized today, you always get this factorization. It doesn't help you very much because I'm going to take the square root of the whole thing. So I've got product, I'm dealing with square roots of cubics. Could be worse, but it's not something I'm used to dealing with by any means. So, but the issue is there's still a well-defined limit, so we can compute that limit if we care to. And so I've just written down here, and so in particular, we get the formula for the generating function for the closed walks at the right-hand end vertex in the chain built from copies of this graph. Okay. So, how are we going for time? Good. I was fussing about Schur complements, and all you really should have got from that is that I can reduce my problem. If I have a graph with 3 tails, then I can reduce my computations to dealing with some 3 by 3 matrix with entries, rational functions. But I want to take things a little further. The thing that physicists are concerned with is what they call a scattering matrix. And I'll define that in a moment. The first thing here is a reminder that we were dealing with this was the Schur complement of the 2 by 2 block of this matrix. Now, it turns out when you're adding tails, well, we've got this psi n, but the limit psi n is just half t squared minus 4. So I know what that is now. Okay. And in fact, if I call that limit psi, then you can see that work out that t is psi plus psi inverse. Okay. And so this, n goes to infinity, that's of psi. So that's going to be, this becomes just everything comes to psi inverse. So for paths, our Schur complement formula leads us to stare at this guy. Okay, psi inverse I minus A minus this mess. Okay. Now, this is where the dirty work is because you're inverting A2. And I said, well, C is small, C is only 3, but this is not going to be n minus 3 by n minus 3. But anyway, but the whole thing is a 3 by 3 matrix. And we define that to be Q of psi. And here we're sort of following the physicists in a sense, that's what they want. Now, what we now define, this is completely arbitrary, a matrix S of psi, and that is Q psi inverse inverted times cube psi. Okay, so this is our definition. This is what the physicists will call a scattering matrix. Okay, and the key property, the magic property of the scattering matrix is that if psi is on the unit circle in the complex plane, it's unitary. That's what I want to show you. So, well, the first thing is that S of psi times S of psi inverse, well, you just write things out. So this is S of psi and this is S of psi inverse, and you see that these two guys product is 1, and then these two guys product is 1, so we get that product as the identity. So first property is that S of psi times S of psi inverse is equal to identity. Well, that's nicely what an invert S. Now, as I wanted to prove that S of psi is unitary, so if I go one step further, the way I set things up, you see that the difference between cube psi and cube psi inverse is just a scalar times I. This tells you that Q of psi and Q of psi inverse commute, because everything commutes with I. And so it follows without too much work, any work really, that if psi is a complex number of norm 1, then Q of psi is normal. And actually there should be a minus sign there. Oops, that's pretty. So basically I'm saying if n is a normal matrix, then n star inverted times n is unitary. And this little calculation here is a proof of that. So if we define S to be this product, then it follows quickly that S is unitary. And so now the point is, whenever I have a graph with these tails, and look at the limit as the tails go to infinity, then I get this, well, you're led to this scattering matrix. Okay, so the point is this matrix is well defined. Whatever assumptions you make or didn't make, I can define this matrix. It's just, it's just linear algebra, there's Q. Okay, so the matrix is well defined. And the claim is that if psi is a root of a complex number of norm 1, then this matrix is unitary, and this gives you, this is the physicists happy because it gives them a gate they can use for their quantum computing. Okay, and now your question is to choose your graph and choose your subset of vertices C so that you get interesting unitaries. And this is well, we don't know very much about that. We know there are interesting examples, but we don't know much more than that. Okay, so I'm going to leave you with one problem. It's a nice little exercise and not particularly difficult to prove that if the vertices A and B and X are cospectral, so if X drop A and X drop B are cospectral, then the first and last vertices of the chain are also cospectral. That follows easily from the formulas we wrote down. I have the innocent questions, are they strongly cospectral? Now, if you haven't seen definition of strongly cospectral, you probably don't care about the question, so I'm not going to go into it. But so the question, simple question, I don't know if they're strongly cospectral. Thought about it a little bit, but nothing fell into place. Okay, so thanks for your attention.